Hi everyone, today we're going to take a look at solving systems of planes. So we're going to take a look at systems with 2 planes and also 3 planes, and we're going to learn how to solve for lines of intersection or points of intersection when dealing with sets of 3 planes, and how we can use elimination to help us do that. So firstly, we're going to take a look at 2 planes, and 2 planes can intersect in 3 different ways. One could be that simply those 2 planes kind of cross each other. They have a line of intersection. So what we'll have is essentially at the end here, we'll create a vector equation of a line where these planes cross over one another. We could also have infinite solutions if our planes are parallel and coincident. And we can also have 0 solutions if our planes are parallel and distinct. So basically what we're going to do when we solve for a system of 2 planes is first we'll always check if the planes are parallel by looking at their normal vectors. And if they're parallel, then we'll determine if they're parallel coincident or parallel distinct. If the normals aren't parallel, that means that your planes, of course, are not parallel, and you're going to find a line of intersection. So we're going to do this by eliminating one variable using elimination, and then we choose one of the remaining variables to equal the parameter t and write the other 2 variables in terms of that parameter t, and that will actually allow us to get the parametric equation of a line. So we're going to take a look at a couple different examples here just so that we can kind of go through those situations there. So the first thing that I'm kind of observing here is the normals of the planes. So the very first thing I always want to do is do a check to see if these planes are parallel or not. So you can see that the normal of the first plane, maybe we'll call this normal 1, is 1, 4, 2. And the normal of the second plane is 2, 8, 4. So I usually like to just kind of decide this by observation, but you can also kind of try to figure it out mathematically. I can actually visibly see right here that if I do 2 times normal 1, it's actually equal to normal 2, making these normals parallel or collinear. So that means that if my normals are parallel, then my planes are parallel. So that would be a yes. Are they parallel? Yes, planes are parallel here. And in order to determine if the planes are parallel and coincident, or in other words, the same plane, or parallel and distinct, we're going to see if the constants of those planes in scalar format follow the same kind of scalar multiple that the normals do. So if the normal of the first plane is half of the normal of the second plane, is the constant half of the normal of the second plane. So if I'm taking each of these things and multiplying by 2 to get to the corresponding coordinate, are we doing the same thing to get from -10 to 6? And of course, we can see that that's not true. So 2 times -10 does not equal -6, and that should mean that the planes are parallel and distinct. So that would be the second step. We just want to check the constants. Oops. Okay, so if this were -20, then they would be parallel and coincident, meaning we have infinite solutions. So these 2 planes are parallel and distinct. So 0 solutions. All right, so same idea for the second one. We are always first going to check if the planes are parallel or not. So I think I can probably just like visibly see here that plane 3 and plane 4, the normals are all being multiplied by 2. So if I say my normal 1, which is 1, 1, -2, times 2 is actually equal to the normal of the second plane, or maybe we'll call this normal 3 and 4 to match up with the planes above. And then I just want to check the constants. That would be my final step. So therefore they are parallel. That's a yes. And then check the constants. And 2 times 2 is in fact equal to the constant from plane number 4 here. So everything's being multiplied by 2. That means these are parallel and coincident, meaning they have infinite solutions. or infinite points of intersection, you could say. Everywhere is a solution. Okay, and I want to take a look at a final set of planes here. So the first thing that we're going to decide is, are they parallel? And usually you can, again, just look at this and see. So this would have to be dividing by half, but we can kind of see that the final pieces of that normal or components of those normals are not half of this first plane here. So 2, -1, 1 is not equal to some scalar multiple of 1, 1, 1. So that means that the planes are not parallel this time. And we're going to go forward with our solving process. So the only other option here is, if the planes aren't parallel, is that they intersect in a single line of intersection. So the instructions say that we're going to use plane 1 and plane 2 to eliminate one variable. So we're going to start with that. And I think that either y or z would be easy to eliminate here because they both have coefficients of 1. So always look to choose the easiest one to eliminate. I think I'm going to eliminate the z's. So I'm just going to stack the equations on top of one another here, and I'm going to subtract. So that's going to leave me with x minus 2y plus 5 equals 0. Okay, so we've eliminated one variable. Then what you're going to do is you're going to choose another variable, either x or y, one of the remaining, to be equal to the parameter t. And because x is kind of like isolated and by itself, I'm actually going to choose y to be the t parameter here, because x will be really easy to isolate in terms of what's left in this equation. So I'm going to let y equal t here. And then we're going to solve for x and z in terms of y equaling t. So you'll kind of see how this works in a second. So just isolating for x here. So we have y equals t, x equals 2t minus 5. And because we now have x and y, we can sub either back into plane 1 or plane 2 to solve for z. So maybe we'll go plane 2. So it'll be x plus y plus z minus 6. So x is 2t minus 5, y is t. And we just want to solve for z in terms of what remains here. So I think we're getting 3t minus 11 plus z, and then just isolate for z here. Let's do this. Okay, so you can kind of see here, if I utilize all of these things, we're going to create the parametric equation of the line of intersection. I'm going to say LOI for line of intersection. So here's our line. We have x equals, I'm going to do the constant first here, it'd be -5 plus t, y equals t, and z equals 11 minus 3t. So if I were to create a vector equation, just as a final answer here, I'd be saying x, y, z is equal to the position vector, which is 5, 0, 11, plus our parameter times, we can see the direction vector kind of buried in there, to -1, 3. So using this one is 0 for the constant here to get our position vector, and then using the coefficients of t to get your direction vector here. So just to kind of show you the 3 examples that we've just done, our very first example was the example where the planes were parallel and distinct. And you can kind of see that these planes are exactly parallel, but they're 2 different planes, so they don't intersect anywhere. Here's our second set of planes that we found to be parallel and coincident, and you can see it really just looks like one plane here, but when I turn this one off, you can kind of see that these are exactly the same plane overlapping. So infinite solutions for those 2. And finally here you can see our two planes from the last example, so clearly these are not parallel, and this kind of gives us a good visual of how these intersect in a line. So it's this line right over here, and I've inputted the line that we found, and we can actually see that that line is correct. So great way to check your work using GeoGebra, or just even to visualize what's going on here. So moving on to intersections of three planes. Three planes can have a variety of different types of solutions, more than two planes can have. So we call systems of planes consistent if there's one or more solutions. So if they intersect in a point, in a line, or with infinite solutions. And we call a system inconsistent if it has no solution. So this is true for three planes and two planes. So here are the scenarios for consistent solutions, meaning we have either a point, a line, or infinite intersections. So all three planes could kind of intersect at a single point. You can kind of see that point right inside here. All three planes could intersect in a line. And what this is going to mean is that when we test the triple scalar product, the normals will actually be coplanar. Whereas when they intersect in a single point, the normals will not be parallel and they'll not be coplanar as well. And then for infinite solutions, you'll notice that the normals of the planes are parallel, and the equations are essentially going to be scalar multiples of one another, just like we saw in example 2b. So what we always check for first is we'll check if the normals are parallel, and we can also predict generally the types of solutions that we could get if the normals are coplanar or not. So a lot of times we'll also check the triple scalar product just to start. So our sets of inconsistent solutions would be if we have two parallel planes and then a third plane that's not parallel. So you can kind of see the plane is intersecting the two other planes in a line of intersection, but there's no common intersection of all three planes together. Okay, similarly, we could have three planes that all intersect each other in different lines, but they don't intersect all at one single line or one single point. So you'll see that the normals here will not be parallel, but in this case, the normals actually are coplanar, so the triple scalar product equals 0. And then the last scenario that we could have is that the planes are parallel and distinct. So if all three lines are parallel and distinct, that could be a situation, or we could even have two planes that are parallel and coincident and a third that's parallel and distinct. So remember, in order for this system to be consistent, they need to all cross at a common area. So if I have two that are coincident, yes, those intersect infinitely, but if the third one is distinct, that means that the system does not have any solutions. So here's what we're going to do to solve for a system of three planes. We're going to check for parallel or coplanar normals to predict possibilities for the solution. If the system doesn't have parallel normals, we're going to eliminate the same variable in two different pairs of equations. You'll see what I mean once we actually get into an example. And then the third thing that we're going to do is eliminate a final variable with our resulting equations from step 2. And there's a couple of things that might happen in that scenario. We might have a system that intersects in a single point, which means that when we try to do this elimination of the final variable, we're going to actually get a value for the variable that remains. We'll sub it back into some of the previous equations from step 2 and then into the original equations to solve for x, y, and z of the point of intersection. If the system is inconsistent, at this point you're going to get an untrue statement. And if the system intersects in a line, at this point you're going to get a true statement, and then we'll have to create the equation of a line similar to how we did with our intersections of two planes. So let's get into a couple examples here. So the first thing that I always want to check is, are my normals parallel? Are there any sets that are parallel? So we're just going to check for parallel planes. And I'm seeing that normal 1 is 2, 1, 6. Normal 2 is 3, 4, 3. And normal 3 is 1, negative 2, -4. So if I'm looking here, even just by kind of visually taking stock of what we have, I'm seeing that none of the normals are parallel. So we have no parallel planes. And then oftentimes what I like to do is just check the triple scalar product between normals 1, 2, and 3. Now this is more of just a prediction as to whether we're going to get a line of intersection versus potentially maybe like 0 intersections or a point of intersection, things like that. So we'll do it for this one. It's not absolutely necessary that you do it, but if you're just simply predicting, rather than like actually solving, it's helpful to do the triple scalar product. So let's do normal 1 cross normal 2, and then we'll dot that with normal 3. So the first part that we want to do is the cross product. And I think most of us are pretty familiar with this at this point, so I'm just going to go kind of quickly here. So we're going to get 3 minus 24. And then we'll get 18 minus 6, and then 8 minus 3. And then we're going to dot that with our final vector. So we're getting -21 minus 24 minus 20. So I can see that this does not equal 0. So what this tells us is that the normals are not coplanar. And a couple things that I can eliminate from my possibilities is that well, I already know that it's not this because I don't have any parallel planes. I know that it's not this because I don't have any parallel planes. I know it's not this because the normals are not coplanar. I also know it's not this because the normals are not coplanar. I know it's not this because the normals are not parallel. And that means that this system intersects at a single point. So that's why it's helpful just to check those two things as you start here. So I should expect we have a single point of intersection. Okay, so let's get into that solving process then. So step 3 is we're going to eliminate the same variable from 2 different sets. So I might choose plane 1 and plane 2, and then plane 1 and plane 3, but it needs to be 2 different sets. There's also a way that you can do this that's kind of similar to what we previously did, but I feel like this is the more efficient way. So if you're looking for maybe other options, you can kind of take a look at what's out there. So I think if we try to eliminate, I'm just looking at what we have here, and maybe we'll try to eliminate the y's. And I'm going to use plane 1, but we have to multiply it by 4 in order to eliminate the y's. So I'm going to do 4 times plane 1, and then we'll do plane 2. So and I'm going to leave plane 2 as it is because now our coefficients of our y's are the same. Okay, and then you just decide whether you're going to add these together or subtract. So we need to subtract because the y's are both positive. The y's should cancel if I've done this correctly, and then I should have some remaining pieces here. So there's one set, and then I'm going to choose a different set. So it can't be plane 1 and plane 2 again. I can do 2 and 3 or 1 and 3. So I think I'm going to use plane 1 and plane 3, and I'm going to multiply plane 1 by 2 in order to make the y's the same. Plane 3 will stay as it is. Okay, and I think because I have a positive y and a negative y here, I'm going to have to add this set. So we're going to get 5x plus 8z minus 23. Okay, so now we've created 2 equations with now 2 unknowns. So I'm going to use these 2 equations here, and I'm going to eliminate a final variable. So then all I'll have left is either x or z. And I'm going to choose this strategically. I have 5x here and 5x here. So that's actually really easy for me to just take these two equations and just stack them on top of each other and eliminate the x's. Okay, sometimes you do have to multiply these by a scalar multiple in order to make your variables the same. So I'm going to eliminate the x's. We'll do subtraction here in order to do that. And that will leave us with z. Okay, so looks like z is equal to 1. And you should expect, if you have a point of intersection, that you end up with, when you go to solve for your kind of like last variable here, or you eliminate your last variable, you should expect to get an actual value for the variable that remains. This step here is kind of the step that's going to indicate to you whether you have a point of intersection, no intersections, or a line of intersection. So when I have a point of intersection, I should expect to get an actual value for the variable that remains here. Okay, so we're going to take this and we're going to sub it back in to one of these two equations. So I'm going to call this equation A and equation B. So I guess we use that here. Sub that back in, solve for x. So I think I'm going to sub z equals 1 into equation B just because it's a little bit simpler, I guess. Doesn't really matter. You should get the same thing either way. And then you just want to solve for x here. So we're getting positive. And then now that we have z and x, we can actually sub both of those into one of our original sets of planes up here. So I think I'm going to sub it into plane number 1 because y is already isolated. It doesn't have a coefficient. So that will probably just make my life a little bit easier. But you should be able to plug it into any one of the three. So let's go ahead. That will be step 5. We're going to sub z equals 1 and x equals 3 into plane 1. And I think we're getting 12 minus 7, and that gives us 5. When we move it to the other side, we get negative 5. So I guess the final step here is just to state the point of intersection, which is 3, negative 5, 1. So basically what this means is that this point is the point that lies on all of the planes above. So a great way to check your answer is to take this point and sub it back into your remaining two planes here and just double check that you get a true statement. You can also sub it back into plane 1 as well and just double check that you get 0 equals 0 when you plug it in. That means the point lies on the plane. So if we take a look over at Geogebra here, here's our set of 3 planes. And you can actually see that was actually a pretty good view that we had there. You can actually see a nice little point of intersection of all 3 planes right there. So I'll show you guys that point, and you can see that's where all of our planes are crossing. Okay, let's take a look at another example here. So the first thing that we're going to do is check for any parallel planes. So normal 1 is 1, negative 5, 2. Normal 2 is 1, 7, negative 2. So I can already see that these two are not parallel. And normal 3, 8, 5, 1. So no sets of these are parallel. So we're not necessarily even looking to see if all of them are parallel, but do we have any sets that are parallel? And that would be a no. So we have no parallel planes for this one. And we can also check the triple scalar product as well. So I'm going to check n normal 1 crossed with normal 2 dotted with normal 3 here quickly. So for the cross product of the first two vectors, I got negative 4 for 12, and then I'm going to dot that with the third. And you'll see here that we're getting negative 32 plus 20 plus 12, which equals 0. So this means that the normals are coplanar. And we can eliminate, from these two sets of information, we can eliminate a couple of the situations that we described previously. So I now know that we don't have a single point of intersection because the normals are coplanar. It could be this. It's definitely not infinite solutions because the normals are not parallel. So this might intersect in a line. It's not this. I don't have any parallel planes. It's not this. I don't have any parallel planes. It could be this. So we could potentially have a consistent or inconsistent system here. So we do need to do a little bit of further solving in order to decide which situation we have. So basically what we found from part 1 and part 2 here is that we either have a line of intersection or kind of multiple lines of intersections of sets of planes, but no one common part of intersection with all 3 planes. So now that we've done our prediction here, we're going to take 2 sets of different planes and choose a variable to eliminate. So we could do the x's here. That's an option. But the z's look like a good option as well. So I think I'm going to go ahead and eliminate the z's. So I'm going to do plane 1 and plane 2 as they are, because those will be easy to eliminate the z's together. And in order to eliminate the z's here, I just need to add these 2 equations. So we're going to get 2x plus 2y minus 4 equals 0. And another set that we can choose here, doesn't really matter, equation 2 and 3 or 1 and 3 I think would work fine. Maybe we'll do plane 2 and 2 times plane 3. Okay, remember guys, there's many different ways to express equations of lines, so many different position vectors that we can get. If we reduce the direction vector, our direction vectors should be similar for all of our answers, but you might get different lines depending on, well, not different lines, but you'll get different equations to represent that line depending on how you choose to go about this. So yeah, if you try it differently than I do right now, you might notice that you get like a different position vector or something like that. All right, so in order to eliminate here, we are just going to add the equations. We'll get 17x plus 17y minus 34 equals 0. So I think we've generated 2 new equations here. I'm going to call this equation A and B. So that was our 3rd step. And for our 4th step, we're going to take both of these and just eliminate a common variable. So if we go for the x's here, I think we can actually make the x's the same if I take equation A and actually multiply it by a half. And basically that's what that's going to do is give me x plus y minus 2 equals 0. And then I'm going to take equation B and just divide it all by 17. So I'm multiplying by 1 over 17. And I'm getting x plus y minus 2 as well. So you're actually noticing here that when we go to, actually I guess we're subtracting the equations, we get a true statement, and that is that 0 equals 0 here. Or we can actually visibly see as well that this equation is a scalar multiple of our other equation here. So what does this mean in terms of what we're trying to solve for? Well, if I get a true statement, remember we talked about how this is the key step in this process that tells us what type of solution we have. So we already decided that either we have a line of intersection or no intersection here. So if I were to get a line of intersection, I would expect to get a true statement here, whereas if I have no intersection, I should expect to get an untrue statement here. So because we got a true statement, this is telling us we have a line of intersection. Okay, so we're going to go to our next step then, and when we have a line of intersection, essentially I'm just going to choose one of the variables that remains from my 3rd step to set as the parameter. So let's say we let x equal the parameter t here. I'm going to actually use this simplified version of the equation. I'm going to plug it into half times equation A, and that's going to mean that I get t plus y minus 2 equals 0, and we just want to eliminate the y, isolate the y, I should say. So y equals 2 minus t. And then we're going to plug that back into one of our original planes. So you're going to choose a plane maybe that is easiest to isolate for z. So I might actually choose plane 3 here and sub in x and y. Okay, so I've subbed this into plane number 3, so we're getting 8t plus 10 minus 5t plus z minus 20. So our job now is just to isolate for z. So I'm getting 3t minus 10, which makes z equal to 10 minus 3t. And that's the last part of the parametric equation for my line of intersection. So as just a final piece here, we're going to create the equation of the line where we let x equal t, y equal 2 minus t, and z ended up equaling 10 minus 3t. So when I create a vector equation of my line, it should be equal to 0 to 10 plus t times the vector 1, negative 1, negative 3. So that should be the solution for our line of intersection. All right, so if we take a look at all of our planes and how they intersect here, you can see they intersect along this yellow line of intersection, and that's the line that we just found. And finally, we're going to take a look at a few last examples. So first step, again, in solving this system of planes is to check whether they're parallel. So normal 1 is equal to 3, 1, negative 2. Normal 2 is equal to 3, negative 5, 1. So I can already see that these two planes are not parallel, plane 1 and plane 2, simply because the normals are not scalar multiples of one another. And then we have 12, 4, negative 8. So these two planes are not parallel, and these two planes are not parallel, but I can see that if I take 4 and multiply it by normal 1, I actually get normal 3, making 2 of the 3 planes parallel. So 2 planes are parallel, third is not. And that essentially means we have this scenario here where I have 2 planes and then a third plane that kind of cuts through these 2 parallel planes. And what this results in is 2 different lines of intersection between sets of planes, but there's no area where all 3 planes intersect. So we can actually say, therefore, the system is inconsistent and basically stop right there. That's why we always want to check first to see if they're parallel, because that can save us a lot of work. Okay, and then we're going to do the same thing for our final example here. So do a parallel check. So here's our 3 normals. You can see that the first 2 are not scalar multiples of one another. And the second 2 are not scalar multiples, and 1 and 3 are also not scalar multiples. So there's no parallel planes. And then if you want, you can do that second step just to double check whether the normals are coplanar or not. Can sometimes be helpful. You don't necessarily have to do this step. I'm just going to do it really quickly to check. So for the cross product of normal 1 and normal 2, I got negative 4, negative 3, negative 1. Then I dotted that with normal 3, and then I ended up getting a dot product of 0. So therefore, in this case, we can say The same thing as we saw in a previous example, which would be that the normals are coplanar. So we actually have two options here between consistent and inconsistent. Either this means there could be a line of intersection, or it could mean that we have kind of that set of three that cross in all different lines, so no intersection in this case. And what we're going to do is go through the solving process just to kind of double check here. So you're going to choose two sets of planes to eliminate a common variable. If I'm looking here, I think that either the x's or the z's would be easy to eliminate. So I'm going to start with, let's say, plane 1 and plane 3 to eliminate x's. Okay, and we'll subtract. So we're going to get 5y minus 3z minus 6. And then for the second one, maybe we'll do 2 times plane 1, and we'll use plane 2. And we're going to subtract. So we're getting 5y minus 3z minus 28. Okay, so we've just generated two new equations. We'll call these equations A and B. And for our next step, we're going to try to eliminate a final common variable. So let's say we go for the y's here. We'll eliminate the y's because they're both 5. And that means we're going to subtract these two equations. So what actually ends up happening here is I actually get 0 on this side. And when I go to solve on the right side, we're actually getting positive 22. So here's where we run into this really important step where we're actually seeing an untrue statement. So of course we know that 0 is not equal to 22. So this should tell us that the system is inconsistent. So we probably have something that kind of looks like this, where all the planes kind of cross in different areas. And of course, if the system is inconsistent, basically what we're saying is that there are no solutions. All right, so finally, if we take a look at this one, we can see that these planes aren't really crossing in a similar area. This is probably the best view where we can see them all kind of crossing in pairs, but we can see that there's no similar kind of area where they all converge. So that's why we ended up getting an untrue statement there, and that's why the system is inconsistent.